Hi everyone, in this video we're going to have a look at graphs of factorized cubics. Okay, so we've got a few different forms that we need to look at and see what the graphs actually do. Okay, so the general form of a cubic is given by f of x equals ax cubed plus bx squared plus cx plus d. Okay, so what information can we get out of that in terms of drawing a graph? Okay, well the a value out here, the coefficient of x cubed, it's like the coefficient of x squared. Okay, it's going to set our shape, whether it's a positive or a negative cubic. Okay, so when a is greater than 0, so when it's positive, it looks like this. Okay, and if you like, you can think of it as if a is positive, then we start off with a positive gradient. Okay, if a is negative or less than 0, we start off with a negative gradient, and it's going to be shaped like this. Okay, the value of d, this constant at the end, is our y-intercept. Okay, but that's all we know. Okay, in this form, you see it'd be pretty hard to draw this function, say this one here, accurately, when all we're saying we know is this general shape and the y-intercept. Okay, this doesn't give us any information about x-intercepts at all. Okay, which is problematic. Okay, that's why what we need to do is, most of the time, is look at a factorized form of a cubic. Okay, and that's given by a out the front of x take x1, x take x2, and x take x3. Now again, that value of a dictates the overall shape of the graph in exactly the same way as what we saw here. Okay, x1, x2, and x3, okay, are all our x-intercepts. Okay, these ones here. Okay, the value for our y-intercept we can still find quite easily. We just have to multiply these values, x1, x2, x3, and a together, and that's going to give our y-intercept, and that's simply the equivalent of saying, well, our x is 0. So what would we be left with? Well, these things multiplied together. Okay, so what else have we got? Okay, we have a little bit more that we can look at. Okay, we have times where our factors are actually repeated. Okay, and we show that by having a squared here. So we've got f of x equals a outside of x take 1 squared times x take 2. Okay, so that's saying again we have a setting the shape, whether it's positive or negative. Okay, our y-intercept is going to be these things multiplied together. Okay, and our x-intercepts are going to be x1 and x2. Okay, the difference here though is we say that x2 is a linear intercept. So in our previous one, we had a series of 3 linear ones, okay, and we say that x1 is really a quadratic intercept, okay, and it's the way it looks on here, okay, and we do have higher ones as well. So our linear one, x2, looks like a straight line where it's intercepting the x-axis, straight line coming through, okay. At x1, however, our repeated one, okay, it looks like a quadratic coming through. It's got that shape of a quadratic, okay, and that's the one that's been repeated. Okay, that's been squared. Okay, finding our values here coming through. Actually, I should note this is actually negatives in there because it's the values as they appear in here that we multiply together to find our y-intercept. Okay, so we don't just take our x-intercepts and multiply them together and times them by this a. Okay, we've got to remember whatever the values are in our actual function that we multiply together by our a as well, and that's going to get our y-intercept. So we have this nice looking one here. Hey, now we can have times where it's one intercept. Now you've seen one intercept before, but that was when we were just looking, at our general cubic that was just y equals x cubed, and it looked like this. Okay, or it might have been moved around a little bit, so it looked like this. Okay, that's fine, but we're talking about one intercept where we've got this distinct shape where we don't have just one spot where our derivative or our gradient is 0. We actually find that we have 2 spots, our turning points. Anyway, what's it look like? Well, we have f of x equals a outside of x take 1. We're always going to have that linear factor. Okay, we have to have at least one x-intercept, okay, for a cubic, and we can have in fact 1, 2, or 3. Okay, here we've got 1, here we've got 2, and our previous one we had 3. Okay, so like usual, a sets the shape, whether it's positive or negative. We only have one x-intercept this time at x equals 1. Okay, and we have our y-intercept is going to be given by a times this negative x1 value, it should have a negative in there, and this constant value here, c. Okay, so basically anything that doesn't have an x in it gets multiplied together to give our y-intercept here. Now, what we know about this quadratic, okay, is that we can't factorize it. Okay, if we could factorize it, okay, then we would get multiple intercepts. So what we can say about that is that the discriminant of this quadratic, okay, is negative. So that's saying that there's no real solutions to this quadratic. Okay, so it doesn't give us any real intercepts. So we're only going to have this one x-intercept from this term here. Right? Now, they also talk a little bit in the textbook about sine diagrams. Now, they're not that big of a deal, okay, but all they are is talking about where the function is positive and where the function is negative. Okay, so for this one here that we were looking at, we would say that we were negative to start off with. Okay, and they like to do something like this with a line representing, say, the x-axis. Okay, and that's at a value of 0 though. So we're negative to start off with. Then at x2 we come up and we become positive all the way up to x1. We're just going to dip down to 0 for a second and still be positive after that. Okay. If, however, we were coming through and we were coming down and back up, like we often do, our sine diagrams are going to change. We're going to be negative to start off with, then positive. Okay, then we're going to go back to negative for a while before becoming positive again up here. Okay, and that's what they talk about with sine diagrams. That side's negative, that side's positive. Okay, it's not too big of a deal. I actually don't like it in here too much because they're just talking about where the function is positive, where in reality we use sine diagrams more when we talk about derivatives and our gradients or slopes of our graphs. But it's in the textbook that we're using, so I wanted to have it in there as well. Okay, we need to actually sketch one of these though. Think about what we could have to do. Right, we need to sketch f of x equals x cubed plus 3x squared, take 4x, take 12. Right, what do we know here? Okay, we know that since this is a positive, okay, we know our shape is going to be something like that. Okay, and we know our y-intercept is negative 12. I haven't drawn it very well here, but our y-intercept is going to come through at negative 12 here. Okay, that's all we know so far. Okay, so we go, well, I can't really sketch this thing because I don't know what it looks like. Okay, does it go like that and only actually have one intercept? Okay, does it come up, touch down, and then through? So it's got 2 intercepts. Okay, or it could be coming right up and through and having 3 intercepts. Okay, and right now we don't know, and we just by looking at it we can't tell. Okay, so this is where we need to apply our division and polynomials skill. So that requires us finding a factor. So we need to try out a few different factors here. So we could try, let's something in 1 here. We're going to get 1 cubed plus 3 times 1 squared. Take 4 times 1. Take 12. Well, that's going to be 1 plus 3. Okay, take 4, take 12. That's definitely not equal to 0. Okay, if we change it to negative 1, well, we're going to be negative 1. Okay, it's still going to be plus 3. Okay, this time will be plus 4. Take 12. Okay, still not equaling 0. Okay, so then we could go, okay, let's try doing 2. 2 cubed plus 3 times 2 squared, take 4 times 2, take 12. And this is 8 plus 12, take 8, take 12. Okay, well that's definitely going to equal 0. So 2 is a factor. Okay, so now we can set up our division of polynomials by going x take 2. Remember, 2 is a factor, we're dividing by x take 2. Okay, so we're going to go x cubed plus 3x squared, take 4x, take 12. Okay, just pointing out too that this is one of our harder type ones. Okay, if we were just, often we'll be given a function that's already factorized and asked to sketch it, but I thought I'll show you the more difficult ones. Okay, so we're going to do our division of polynomials. So we go x cubed divided by x is going to leave us with x squared. Multiply back through, x squared times x gives us x cubed. X squared times negative 2 gives us negative 2x. Bracket, bracket, take away line underneath. Do our subtraction, x cubed take x cubed is 0. 3x squared take sorry, that should be 2x squared. 3x squared take negative 2x squared will give us 5x squared. Now we take 4x down and our 12 down as well. Now we start over with a new question. Okay, so 5x squared divided by x is going to leave us with 5x. Multiply back through gives us 5x squared, take 10x. Bracket, bracket, take away line underneath. Do the subtraction, these cancel out. Negative 4 take negative 10 will give us positive 6x, take 12. Okay, x into 6x gives us 6. Multiply back through, we're going to get 6x, take 12. Bracket, bracket, take away line underneath. And we see that these do in fact cancel out. So what we've done there is we've been able to factorize it so far and say that we've got x take 2 x squared plus 5x plus 6. Okay, so right now though we could have this situation where it's coming like that and we've only got one linear factor. Okay, this could be a perfect square so that we've still got 2. Okay, or we could be that this could factorize and we're going to have 3 linear factors. Okay, so we need to look at our x squared a little bit and see if we can factorize it. Okay, this one we can see that we can actually quite easily do it and say that we've got x take 2, x plus 2, and x plus 3. Okay, this factorizes quite easily. If you weren't sure though, you could do our discriminant, which is our b squared minus 4ac, just using our values for a, b, and c from here. Okay, and that would have shown that that was a positive number. Okay, hence we could factorize it and get trivial solutions. Okay, so now we've got probably enough to sketch our function. Okay, so we know we're going through negative 12. Okay, we know, oh hang on, we've got to finish this off. Sorry, we've factorized it, we haven't actually worked out what our x-intercepts are. Okay, that's through our null factor law, and simply we're setting each of these equal to 0. So we're going to get 2, negative 2, and negative 3. Okay, so I come through here at negative 2, and negative 3, and also up here at positive 2. So we can now, and we know we're going through negative 12, remember, and we know that we're positive, so we're shaped like that. So we can come up, do our intercepts, back down, and we're going to be something like this. Okay. Now you might have been tempted to go and say that this minimum was here at negative 12 because it's halfway between negative 2 and positive 2. Okay, but in fact, remember with our cubics that doesn't hold true. So that's true with our quadratics. Okay, that our minimums and our maximums are halfway between our x-intercepts. Doesn't hold true for our cubics. Okay, at this stage we're not too worried if you accidentally get those in the slightly wrong spot though. Okay, we're not too worried about that just yet. So look, that's a good example of about as hard as they get. As I said, most of the time you're going to be given them in a factorized form or a form where you can always sketch them. Okay, so hopefully that's enough to get you through the questions on this work.